live now. Anytime soon we will be live. Yep. Okay, I don't know what's really going on here, but we are live. Discord for some reason is down today, so I'm not sure, but it's okay, I guess. Just wanted to quickly go live, discuss. I I'm not able to share this on Discord. I really, really hope that some people join. I can quickly message Nehal. Oh, hi, Dave. I just thought, okay, today is a fresh start. I just restarted a few things and I'll try to motivate myself to do it. But anyways, I do have a good topic to talk about today. Dave, one question, is Discord working for you? Hi, Swanan, what's up? Thank you so much for joining here. What's up? What's up, everyone? Is Discord working for you, Dave? If it is working, can you do me a favor? Can you please play Holy? Okay, yeah, thanks. Yep, I thought so. Okay, sounds good. Not loading, yeah. And that's like something. So I wanted to update it there, but it was not loading. So I'm like, okay, let it be. I am not with my mic today because I lost the cable of it, so I have to find it. I just thought like, okay, at least let's stream and quickly talk about a very interesting thing that I was reading yesterday, and probably is worth it. So I hope you guys also like it. Will ta-da, okay, there you go. Hope you guys can see the screen. Everything is good. Let me also make sure that I do get to see your chats here. Okay. All right. Where is my, okay. Did it close? Yeah, it closed. Okay. All right. I'm gonna wait for this to connect. Yep, there you go. Okay. You guys can see the screen. You guys can see everything, right? So it's visible to you, is it? God level. Hello, Mohit. What's up, man? What's up? How are you? Thank you so much for joining. Yes, okay, it's loading to you. Give me 1 second. Let me also make sure that, yep, there you go. Awesome. Oh, not this one, sorry. Yes, it is. Okay. Sounds great, guys. So today it's a very interesting topic, right? Today we are going to discuss about cache management. Okay. And I will talk about why. Okay, and it's gonna come to you all as a surprise that okay, guys, like it's that interesting. So this cache management, the way for you, I want you guys first of all to think about it, that how does it work, right? Like what's the cache for? I know there are multiple levels for it, L1, L2, and depends on the systems and all, like the architecture, there could be more, right? Cache, I used to call it cache management, but yeah, it's cache as well. I mean, depends. So when it comes with management, I call it cache management, but generally I call it cache, L1 cache, L2 cache, right? It's very weird. But anyways, like okay, let's call it cache for the consistency purposes. But think about it now. So you have multiple things, right? So let's say you have an automatic cache. Okay, sorry. Yeah, I think I'm calling it cache all this time. Cache. Nahin. So think about it, right? So what this means is so there's like similar as GC, right? So there's manual and there's auto, right? There's manual and there's auto. Similarly for cache management, for now assume that it's automatic. In that case, what does it mean? Right? So you have int a equal to 3, you have b equal to 4, right? Now here I'm doing a plus b, right? And I store this in C. Now ideally what this happens is like when you're computing this already and you're trying to, let's say you're in a for loop, right? And you are doing it again and again, you're doing the same computation again and again. Now compiler should be smart enough during the compilation, right? When you're compiling, it knows that okay, this a and b is always the same. So of course, like when you apply some optimization levels and all, it will simplify it. That is true, right? So what this basically does is when you have c equal to a plus b, it's gonna store that in cache and say that hey, let's not recompute, right? So cache is more like okay, how can I just do this memoization, right? So but cache is basically a memory storage. So whenever I say that, okay, it's like memorization makes use of cache or something, right? Or not necessarily cache, but it's just the whole concept is like do not recompute something, right? Now think about it. When I'm saying that, hey, over here, I'm gonna say C equal to C into C, right? So this means that I'm calculating C square again. Okay. So what this means, I'm accessing A, I'm accessing B, and I'm accessing C back again, right? So I'm accessing these three objects again and again, again and again, again and again, and there is like D equal to 10. Now we introduce another variable over here. If you guys see, I think I should have it like this. Probably it's better. Yeah, I think this is going to be better for you all, right? So what we did, we introduced one more variable called D equal to 10. So right now we have A, we have B, we have C, and we have D. Now all these three are regularly accessed, right? And this is not accessed at all. Now, given that in cache memory, like in general, you still have space for us to store D, right? Let's say like we did say that, okay, I want us to store D in the cache as well. Okay, now we are doing that, but it's not exist at all. That means like we are kind of say we want ABC to be more reachable to us compared to D. Now think about it, guys. How would you want to do this in the fastest possible way? What kind of data structure would you use, right? So I wanted to end like at the end, yes, that this video is again about a very interesting data structure I wanted to talk about. But now, for now, think that how will you do that? What's the fastest way? So what are the requirements, right? Let's think about this. First of all, my voice is good, right, guys? Anyone, Dave, Mohit, Swanand, anyone here who can make sure that please let me know if my voice is okay. Anyone say yes, say no. Yep, yep. Okay, thank you, Mohit. Um, Now the thing is, it's good. Okay, okay. Right. So the very interesting thing is, what are the requirements for us to have this cache, right? So whenever we want something, that means when we are searching, it should be fast. Why? Because of course, cache in a memory sense, it is very fast. That is true. But when you are trying to manage this, like you see, at the end you need to store the pointers, right? You can't just have L1 mem cache and say that okay, L1 cache is like an unordered map. No, the reason cache is faster is because in the memory layout, it has these access like the similarly like registers are closer and all or whatever, they are faster and all. So similarly cache in general in the sense of memory layout is faster, but you still need to store that, okay, where is A, where is B, where is C, where is D, right? How would you store this is a whole data structure thing, right? That is like how would you do in a programming sense, right? So now, so this search should be fast enough for us. So that's one priority. The second is when you're inserting, we should not compromise as well. We want this to be fast as well, because when you're storing something in cache, you want it to be fast. Like that's the whole point as well, because insertions are very regular in cache as well, right? So that is there. Deletions should be fast as well, right? So here we cannot optimize. There's a train passing by. We cannot optimize mostly on anything because we need to kind of clean up cache as well as we go along, right? We cannot keep filling cache and say that, okay, now we're cleaning up. Please give us some time, right? How would you do that? Now, whenever these all fast come, right? So think about at this point, I know that no data structure will allow me these many things unless and until I have a tree. Okay. And why am I talking about a tree here is very interesting. Okay. First of all, these are all fast because they give you O of log n, right? Why? Because a balanced binary search tree is always going to give me these like amortized like time complexities are always going to be O of log n, right? So that is there. That's why like if you think about it, like B tree and all is there, right? So the like we use them in database indexing and all. So we are going to use this because insertion is going to be fast, deletion is going to be fast, and searching is going to be fast. Now I know like for those people who do not know what is the time complexity of these like doing in tree, how will they still realize that it's a tree problem, right? Um, think about it. Any memory layout, wherever you store, over here, what are we looking for? We are looking for the most frequent to come first, because in cache, we want it to be mostly like recently. whatever we are trying to access, we want it to be quickly accessible. So last time when we access C, and the next time we are trying to access C again, so this time it should be faster because we just recently accessed. There is one way. So this is called recently accessed, right? And the other point is that, okay, even though you access C recently and you're trying to access C again, it may not be the fastest because the most frequently accessed is A. So this is about most frequent. So this is on the frequency. Okay. Oh, I'm sorry, you guys cannot see. Let me, yeah, there you go, right? So over here, there are a couple of things that we can do. First is recently access. The second is like, of course, depends on the frequency. How frequently are you accessing something, right? Now, this is what I was going through, and I realized, okay, there's a data structure called splay tree for this. So what does it do? Right, so splay tree is very simple thing. Like, don't worry too much about it. First of all, um, splay tree, what does it do is you try accessing something. It's a balanced, it's not a balanced, but it's kind of a self-balanced binary search tree, by the way, guys. Okay, and I'll come to how is it not really self-balanced, but in general, like you can say that it will balance itself out. We will talk about it, right? So um, the way it works is you insert something right now. Let's say that, okay, let me actually make it better. So let's say you have X, you have A, you have Y, you have B, and you have C. So this is what you have, right? Now in the next operation, you are trying to access A. A equal to, you are doing A equal to A plus B. Now the recently accesses A. So what does it do? So it brings A to the top. That means because A is the most recently accessed, what will it do? It will bring A to the top and like it will rotate itself and all. So what it will do, I don't know what will be the output. I'm not really very curious how does the rotation happen, but this rotation will happen, right? So what does it do? It always brings the most recently accessed to the node, which is the root node. Okay, so that helps is because it will have like it, I mean the whole worst case can still, you can still call it like O of login, but whatever that was recently accessed, it will be the fastest to access in this cache memory like management system as well. So over here, if I'm trying to access A, it makes sense because now A is the root node. I will quickly access, I'll try to iterate through it. I'll call the search operation, right? And I'll find that, okay, A is here, just return. So it will be the fastest operation because now A is the recently accessed, right? Does it make sense to you all? You guys are getting? So this is how caches are management at the OS level or what? Yeah, right. And I'm going to show this to you. Let's see. This is like not necessarily OS level because think that cache memory, the way it works is it's mostly on the programming level, like what kind of cache library you use. So like I don't think it's on the OS level. Depends, like maybe in threading and all they are doing that part. I have not explored that, but it's mostly on the compilers part. Like LLVM will have um, some splay tree implementation and all, and I'm gonna show it to you all now. Okay, hello, hi Pratika, thank you so much for joining. See, like let's get out of this now. By the way, like just for your like in case this comes up in the interviews as well. See, this is how you kind of make it interesting, right? So play tree, in case they ask you in the interviews, I would not know how to perform the rotations and all, but then there are multiple kind of rotations that you can call it. So there's like zig, there's zag. So there are these two terms. This is called left rotation. This is called right rotation. So there are combinations of it. What it calls is zigzag. Okay, then there is zigzag. Then there is zag. Okay, then there is zag. Okay, so I think you all get it, like LL, LR, I think RR, right? And then this is RL. Okay, so it's like left right rotation and all. And I'm honestly speaking, I was not curious that, okay, how will these rotations be implemented, because it's an implementation detail and I can always learn that, okay, यहाँ पे we have A, we have X, so I wanted to rotate right towards. If I had something here, then it will be left rotation and all. Like these are very simple things that we can understand later on, but I'm just saying that there are different type of rotations that are possible. What is very interesting is, and as I said, this is a very basic implementation. Many libraries modify this according to their use cases. And like for me, for example, I was very curious that, okay, something that is most recently accessed should be on the top, but I would prefer that it's also should be on the basis of frequency. So think about it, okay? What they're basically doing is you have A, B, C, D, and E. Now, next time you are doing C equal to C plus B in your program. Now, here the compiler understood that, okay, you are trying to access C. So C is right now the most recently accessed, okay? Now it will try to bring C to the top. Okay. So every time this C is done, because it will search in the cache as well when it's trying to access C here, it's trying to access B here, then it's trying to access C to store C as well. So when it is doing C, right, search operation here, every time a search operation is done, it looks for like the root node. If the root node is C, it will immediately return. But if it is not, it will iterate through the balanced binary search tree. That's why it's O of log n. Now what it will do, it will search, it will find, but it will also rotate and try to bring C to the top, right? It will return something like this. And I'm not sure if the output will be like this, but definitely C will be on the top now because it's the most recently accessed, right? So my point was, let's also consider which was the penultimate one. B was also the one. So like, I mean, B should be closer as well, which it already is because of the way I wrote the original search tree. But there are multiple things given how you want your cache memory to work. Okay, so it's really on the programming language and the library. Now let's actually go and read about it, right? I will show you guys how to use ChatGPT the right way. Okay. Now give me 1 second. I will have to share my screen, the ChatGPT one. So I'm gonna hide my okay, yeah. All right, guys. Give me 1 second because I'll have to open ChatGPT and I want to make sure that it's clean for you guys. Yeah, I think it's clean. Okay. You guys can see my screen now. Yeah. Can you guys see the screen? Yes, you can, right? So I'm assuming. And how many? I'm just kind of curious. Hey, are you guys here? Keep keep saying hi in the chat, guys. It's okay. Discord is down, so I cannot. Okay, perfect. All right. So now what you do is, okay, explain me the real use cases where splay tree is used. Okay, and share some code snippets from their libraries. Yeah, Discord is still down. Yep, sad. Okay, let me. Yeah, there you go. Right, so as you can see, it will cache implementation, as I said, temporal locality, we discussed about it, right? So it will share some code snippets as well. How will it work, right? So as I said, like it will search, it will go and display, and what does display do? If root dot key equal to key, then it says return equal to return root, right? All these things, memory management, data compression, router tables, and all. Now you see, like, so libraries that use play trees, GNU lib std c++, in internals, data structure, Linux kernel, virtual memory and cache subsystems. You can see rope data structure, that is an alternative to string that also uses it. Okay, can you share the link of such libraries? Right, so let's ask what libraries that actually use it. So splay tree by w8r, splay tree. Okay, no, this is not what I want. No, share the open source libraries that use Playtree, right? I remember seeing one of those. I'm waiting for it to give me that, like it's still giving the implementation. There you go. So Redis rope module, the Redis module introduces a native data type for manipulating large strings efficiently. It employs play trees to manage and balance the underlying data structure, enhancing the performance of string operations, guys. Okay, now I will show you, like, see, it gave us this, right? Now we don't, maybe, let's just see, yeah. The ropes in this module are backed by spray trees, which are self-adjusting data structure that has logarithmic amortized worst case performance, right? I'll show you now how to do it, right? So over here you have chat with Copilot. Click on this and then try to search, is play tree used in this code base? Where is it used? Ignore the typo, I think we don't. So now just use this conversation. Now what it will do is it will share the code files wherever it is used. Okay, meanwhile let's also go to the other one. Extra collections, that's okay. Tree playground, that's not what we want. What are the cache memory management libraries that use split tree? Yeah, there you go, right? So what it says describes the ropes. So here README does mention this, and if you go as well, it will share that README has it. Then implementation of the rope data structure based on splay trees, right? So it's written in Zig, and if you see over here, I think they use, yeah, a rope data structure based on splay tree. The minimum number of bytes stored in a splay tree node, the capacity of splay tree node in bytes. A node in the splay tree, as you can see, like they have a parent, they have child nodes and all. They have update, they have connect, they have ROT. So, I mean, see, this all is using splay. Access the splay tree at an index, returning the new root, right? So, you can imagine that even rope data structure that, I mean, if you guys have not known, this is alternative to string as well. So, it's important. And even the like main.zig has implementation to splay. Like, see, like, I think they are looking for splay like usage and all. So, sometimes it's just worth it to look for it. I'm gonna also share cache management using split trees. See, there you go, right? So there's one more library that I think they have made a demo of this, but I think, wait, I am looking for any open source libraries that use play. So LLVM does use it as well, I remember. So let's look for Redis rope ho gaya, free playground. Let's keep asking because I was looking for one more. It's not going further. Yeah, so I think it's like, see, it's very interesting. It actually does search for splay tree, libdict, splay tree implementation, data structures, ERL splay tree, IP address finder using splay tree. Okay. With the help of splay tree data structure, we could create a tree whose nodes are embedded with the IP address of the device that are connected to a specific network router. In our code, we have taken 11 devices connected to one network router, and so there would be some common part in the IP address of each of the devices. See, like you guys like should probably read a bit about it as well. There will be more things as well. Mm, any web cache management, so that I think sometimes it just gives different results. That's unfortunate. Okay, just give me 1 second. Let me actually look at my search history because I do want to show it to you all. Um, yeah, there you go, Squid library. It's kind of weird that they were not showing it. So there you go, right? So this Squid library is there, Squid cache, right? So this is there. So this is web proxy cache. Okay, it's still active. It is 2.2K stars. Okay, and what is it? Is this whatever it's web proxy cache. Okay, and if you so over here it's very hard to find. So what I just did, I asked ChatGPT. Okay, I mean I asked this Copilot, does it use Playtree? Yeah, and just kind of ask it, and it's very interesting, right? It does give you a very relevant result. So if you do this, I'm gonna wait for this to be done. Yeah, there you go, right? So they have includes play.h h test suite. They have some testing for Play as well. So you can see like they are probably test type safety Play containers, int mode and all. They are doing all of this, and they have Splay inserter. Then they have Splay.cc. So they have all the implementations as well. Helps populate a Splay tree with configured ACL parameter values and all, right? So they have all the declarations here. Probably, yeah, this is a header file, and they have the implementation in libsplay.cc as well. And where is it? Should be somewhere. Yeah, I think probably it's in the preview mode, so it has not given to all of the users. Or it's like Copilot Premium you need to have. I'm not sure, buddy, but it's like even if you don't have it, generally like what you can do is you can do github.dev, right, and kind of search for this play keyword. Like I would do that. Like it's also like don't worry, it's like don't feel that way, but like even you can do that. So okay, just to use my keyword. So it's like it's a very interesting feature. Like I mean, I'm not sure what took them so long. So as you can see, like libsplay.cc, and guys, what happens, right? As I was telling you, so what they always do is now they try to modify their things according to their use case. So you will always find that this is like credits. So they have a credits file as well. So you guys should take a look, but I haven't used it. Yeah, it's a very nice feature. Like when the library is huge, you can ask. Yeah, cursor can do this as well. Like see, we need to move forward and try to use these editors for ourselves. But as I said, like there are more things to even look at. Like so they have like different things over here. You can see what algorithm it uses now. Now what I'll say, Wikipedia page of Splay Tree. Let's just ask it to give us that. Now, now what you guys do is actually, array, yaar, I hope it opened. Yeah, there you go. Right. So look at this. So it was invented in 1985. Daniel Dominic Slater and Robert, like all these people. But if you really go, so as I said, like zig step, zig step, zigzag, join, split, insertion. Now, very interesting thing, right? So whenever this comes up, what I do is, um, I look at the original research paper. So this came up in Self-Organizing Journal of October 1978. Yeah, I think this is where I was looking for probably um, self-organizing. But yep, there you go. Right. So when you open this PDF, this is very interesting, guys. Okay. So this is self-organizing binary search tree, right? Given a set of n records with an ordering on their keys and given the independent probabilities of their being accessed, it is well known that a binary search tree of minimum cost can be constructed in O of n square. In this paper, we consider the case in which we are not given the underlying probabilities. Hence, we would like to modify the binary search tree dynamically so that the average search time will be as small as possible. Okay, and like they kind of discuss what are the use cases. It's very, very nicely written, right? A bound on the cost of the move to the root. So as I said, like what they're basically doing is simple exchange transformation. This is like basically means rotation. A was here, now A is on the top, right? So if A is like requested now, so A is the most recent one. So it is transformed to the root of the tree. Um, and they have all the proofs and all, they have all the theorems, they have all the lemmas and all. Like it's very, very interesting, the simple exchange heuristic. It is very interesting. If you guys like want to go through it, it's amazing. Um, I would say that definitely look at this. Like it gives you a really, really, really good outlook of how things work. Like it was a good read. I have not read it like the mathematic part of it, but I've read it like yesterday. I was reading through the main part, how does it work and all. So this was very good. Okay, so you guys should take a look. These things help like University of Waterloo. Um, it's interesting. And then I think one thing I was looking for is semi-splaying as well. So what does semi-splaying mean, right? So it's very interesting. So the results show that semi-splaying, which was introduced in the same paper as splaying, performs better than splaying under almost all possible conditions. So semi-splaying matlab kya hota hai? You don't move a node to the root. You move a node to kind of half. So because like moving to the root is an expensive operation, let's say if it is at very bottom, so you kind of just move thoda to the top of it to be closer to the root, but you don't move it to be the root. So that's like very interesting thing, right? And if the like whole tree is very huge, because it's possible that cache is not necessarily will have only 5 nodes, it will have let's say thousands of nodes. Then you want it to just go closer to the root. That's the whole point. So they also like wrote a paper on how semi-splaying is important, right? So semi-splaying just means like do it thoda and just get done with it, right? So these are all very interesting things. You guys should please take a look at it. Um, and see like how was it invented, who invented and all. Definitely read about it. Very interesting things. So this is the one, I don't know, you guys should take a look. Anyways, this is mostly it, guys. I wanted to quickly touch upon it. How was it for you all? Did you guys enjoy? 1 second, give me 1 second. Let me quickly address one thing. Yes, sorry. Yeah, let me turn it on. Did you enjoy the stream today? Yeah, I wanted to touch upon like last night I spent a lot of time, so I was up until 2 or 3. And we were like going through this. Like I wanted to touch upon, I can actually show the notes from yesterday. Wait, where are the? So I did discuss here. There you go. Right, I can. It's a very. It's not an interesting language. Discord is back. Okay. So this was like all night I was doing ki okay root left right play करेंगे and all. So these are like all the notes I was writing. It's, so you see. So two should be on the top right and also I was I was going through this. These are all my notes from yesterday. Ta-da! So I thought like I will talk about this. Even Linux kernel virtual memory management system uses this. Discord is back. I will check it out. Uh, Let me go back to our chat. This is what nerds in Bangalore do on a Saturday night. अच्छा था. I mean, yeah, like uh, चलता है like God level. हाँ. So my only suggestion to everyone is like, data structures are very interesting things. And like I wanted to cover, okay, think about why would you need a balanced binary search tree? Like, see, the whole point of balanced binary search tree is because you cannot have a skewed binary search tree because in that case, worst case becomes O of n. It's possible like all the n nodes will be skewed on the left side and you will have to iterate the whole part, right? So balanced and self-balanced binary search tree is very important because you don't have to spend time in balancing it out. Like left and right may same kind of height or levels so it is expensive, right? So these are very interesting things. Like I always suggest like people to think in that fashion and it helps. I don't think anyone will even ask these in the interviews as well because but they can ask like can you design this LRU and all, right? Least recently used cache memory or something. But I would always say like think about it. कैसे करना है? Like don't ऐसे कि यार कहीं पढ़ा था, oh shit yes this is the question, right? हम लोग काफी लोग कुछ नहीं करते कि सर एक सेकंड याद आ रहा है yes yes सही ट्री वाला क्वेश्चन है ना? यस यस याद आ गया, लाइक वो बोलते हैं वी कैन डू इट यूजिंग लिंक लिस्ट, अरे यार शिट यस सही लिंक लिस्ट वाला क्वेश्चन नहीं करना है ये सब. ये यही है लाइक इफ एनीवन डज दैट इन फ्रंट ऑफ मी इन द इंटरव्यू आई अंडरस्टैंड बट आई विल लाफ कि नहीं भाई द क्वेश्चन इज फॉर प्रॉब्लम सॉल्विंग. लाइक वो नहीं होता सर एक सेकंड रिकॉल कर रहा हूँ नहीं याद आ रहा है अरे यार यस ये हैश मैप्स राइट. लाइक think about it, always think about it and then करो कि कैसे करना है. like there is nothing that a human being has not one three to hit hard. वही ना मतलब यही पॉइंट है कि सब लोग गलत गलत तरीके से करते हैं. like I and as I said like I was always very much against लीड कोड. पता है क्यों? क्योंकि लोगों ने उसकी इमेज खराब करी हुई है. like इन भैया शीट से भैया शीट क्वेश्चन 6 हाँ लाइक एग्जैक्टली लाइक क्वेश्चन आएगा ना. यस यार ये लीड कोड का 100 वाला क्वेश्चन है, याद नहीं आ रहा सर आप मुझे एक बार लीड कोड का वो शीट दिखा दो, मुझे पता है टॉप से 100 वाला इज गोना बी एरे क्वेश्चन. आप फिर मैं देखो आंसर बता दूंगा. That's what we do, right? Like even in, it's not just in lead code. Like CBSE board exams, half of the people also do that. ये organic का अगर ये वो वाला क्वेश्चन है, पहली गलती तो लोग पहले ही कोड करने बैठ जाते हैं, not figure out how to हाँ right exactly. See like if I will ask you guys, okay, I will be honest, okay, can I rant a bit about Google today? Can I take that time to rant a bit about Google, guys? Because I want to do that, right? So this was happening, ठीक है? Yesterday like when we were driving, so I realized कि बहुत Google Map has huge caliber. Okay, Google Maps has no competition at all for Android people. Like Apple Maps होगा and app even people on Apple iPhones they still use Google Maps. ठीक है? The problem that comes up is first of all recently they introduced this feature where they will tell you that you have to take a bridge and you don't have to go straight. How fucking difficult was it to introduce this feature? Tell me, in this generation, how many years did it take them to introduce this feature? You have to take the bridge, you don't have to go left. You have to take the bridge. There is an option for you to take the bridge. राइट, लाइक खुद सोचो, हाउ डिफिकल्ट वाज इट, एंड उसको उन्होंने इतना बड़ा फीचर बनाया है। भाई, इट्स अ वेरी वेरी सिंपल फीचर, नाउ आई एम टेलिंग यू, imagine there's a there's a there's a pregnant woman in the car, ठीक है, and a guy is driving, so they went to Google Maps, they said I want to go to the hospital, ठीक है, अब pregnancy में it's not very urgent, when they know कि okay she is about to hit the final run, but problem क्या होती है ना, Google Maps just shows कि okay this is the fastest route, right? Problem तब होती है when Google Maps does not show you it's the most comfortable route. I don't want to take the fastest route right now. Show me जहाँ पे मिनिमम नंबर ऑफ पॉट होल्स होंगे या फिर हाईवे रहेगा. शो मी द रूट दैट इज कंफर्टेबल टू मी. हाउ मच डज इट टेक फॉर यू टू हैव, इतने सारे सेटेलाइट्स हैं, इतना सब कुछ है. आई वॉन्ट कि ट्रैफिक रहे तो रहे, माई वाइफ शुड नॉट हैव द स्ट्रगल ऑफ गोइंग थ्रू पॉट होल्स, राइट? सो ये सब चीजें कितना कितना इंटरेस्टिंग फीचर है. राइट नाउ इफ आई एम ड्राइविंग अ कार एंड इट इज लाइक थोड़ा बिगर, so I should have an option to ask the like Google Map कि okay give me a road, like give me somewhere like जहाँ पे highways के through मैं go through करूँ. I don't want to go through narrow roads, like that's the whole point कि मुझे नई narrow, और वो Google Maps अभी भी दिखाता है कि यहाँ से लेफ्ट ले लो. भाई मेरी गाड़ी को लेफ्ट लेने के लिए जगह ही नहीं है, राइट? एंड आई एंड अप गोइंग देयर एंड आई रियलाइज कि नहीं यार, टू साइडेड रोड है, वहां पे बाइक्स ट्रक वर्क सब जा रहे हैं, एंड आई कैन नॉट टेक इट, देन आई हैव टू टेक रिवर्स. इट शुड शो मी कि योर कार इज दिस मच, यू हैव फेस दिस प्रॉब्लम, यू शुड गो थ्रू दैट, राइट? सो दैट इज वेयर हमारे डेवलपर्स, प्रोजेक्ट मैनेजमेंट्स एंड ऑल सब गलत जाते हैं. दे डोंट थिंक अबाउट कि what are the features, कब इनोवेट करेंगे. दे हैव टेकन सो लॉन्ग टू इनोवेट दीज बेसिक फीचर्स, ठीक है, लाइक दैट्स ऑल आई एम सेइंग. So I think personally there is so much to innovate, there's so much to improve, but they are not able to do it, and that is one of the reasons why why I really want कि Google Maps को कोई compete करे. पता नहीं यार, like that's all I'm saying, right? कि competitor ही नहीं है. So Google Maps enjoy कर रहे हैं. Entire and that's what I'm saying. पता है क्या कि AI इतना स्मार्ट होता है कि when I have taken a route जहाँ पे रोड का डायमेंशन ये है, I know कि मुझे काफी रिवर्स लेना पड़ा, मुझे ये करना पड़ा. Google Maps should predict कि okay this road was not for you. The next time I take that route, it should say कि the last time you went through this road, you were not comfortable. Personalized होना चाहिए. Google Maps should be personalized. And of course, you can disable it if you would want. So it's an optional feature, right? It's an opt-in feature. You want it, you take it. You don't want it, keep the original one. कितने सारे features हैं that you can enter and make Google Maps really personalized. ठीक है, भाड़ में जा. Just typical ranting, sorry. I did not read your message, Dave, yesterday. I'm sorry. Like, I was not opening GitHub, sorry, Discord last night. But hope today's stream was good. Did you guys enjoy the data structure thing? Was it good? Did you guys learn something new today? Can you guys give me a quick yay? Yep, Pratik, thank you. Swanand, Dev, Mohit, Wankhede sir. Yes, sir. Okay, nice. But yeah, guys, keep asking ChatGPT some interesting questions. मैं नहीं बताऊंगा, बेशरम इंसान. मिलो आज तुम लोग काउंटर स्ट्राइक में, बताता हूँ तुम लोग को. मैं भी नहीं बताऊंगा. ठीक है भाई, ठीक है. यार सॉरी अबाउट दिस माइक, बाय द वे उसका केबल खो गई है. आई वाज चेंजिंग, सो लाइक अपने नहीं होते लड़, फॉर बॉयज इट्स लाइक इवन अ हेयर कट इज अ रीस्टार्ट इन लाइफ. तो आई जस्ट वी जस्ट चेंज्ड द टेबल यस्टरडे एंड सेड लाइक थोड़ा पोजीशन चेंज करते हैं, लाइफ को रीसेट मारते हैं, थिंकिंग अबाउट इट. तो ये क्या, वो 80,000 वाला माइक किधर है भाई? मेरा 80,000 वाला नहीं है. कीबोर्ड था 80,000 वाला, वो भी अंदर है. माइक है इधर पास में, बट केबल उसकी वापस ऑर्डर करनी पड़ेगी शायद, या ढूंढनी पड़ेगी. चांद सिफारिश जो करता हमारी। 5 लाख का सेटअप है। ते- 1.5 लाख वाला, अरे बाप रे भाई साहब, रुक जाओ रुक जाओ। ये सब चीजें पब्लिकली बोल के मेरी क्यों क्यों मेरी मार रहे हो भाई तुम लोग, हाँ? Dave, you do understand this much Hindi, right? I think you don't have any problem, na? You do. Sorry, sometimes I end up talking in Hindi. मुझको राणा जी माफ करना। केबल गुम जाती है तो अपने भाई डायरेक्ट न्यू माइक खरीद लेता है। अरे भाई, नहीं भाई नहीं, वो पुराने दिन, वो हसीन दिन, बहुत प्यारा है। If you guys have never heard this, this वो पुराने दिन वो सुहाने दिन, it's really nice. You guys should take a look. I'll share the link. It's a it's a nice melody. चलो, anyways guys, everything is good. I had NVIDIA will soon file bankruptcy. नहीं भाई, कुछ नहीं है ऐसा। करेगा तो करेगा भाई, अपने को क्या लेना देना है, लाइक देखो यार, लाइक हाँ, लाइक देखो, इतना तो मैं समझता हूँ कि देखो, NVIDIA was at the end, NVIDIA is a Stree 1 a good movie. Yep, yep. Stree 1 is a really good movie because of Stree 2 is also a good movie. I think Stree 1 is an excellent piece of art. I loved it. Better than 2. Yeah, kind of. Many people think that it's better than 2. But I loved 2 as well यार, कहीं ना कहीं क्योंकि कुछ cameos and all were unexpected. And मुझे अच्छा लगा था, I liked it. And Dave, guys, suggest me a series quickly that is available on Netflix. Suggest me a series. Suggest me a series. का फर्स्ट हाफ ही अच्छा था, अच्छा। हाँ मतलब, बट मिस वन लाइक फिर भी लाइक स्त्री टू वाज गुड। मजा आया था, लाइक लाइक सो आई वाज लाइक 2 times इन सिनेमास। नहीं, केटा वन ही देखता है यार, मैं देख बहुत टाइम हो गया, आई थिंक 1 to 1। बेटर कॉल सॉल। अच्छा, ये सीरीज का नाम है क्या? ओके, ठीक है, लेट मी टेक अ नोट। बेटर, सो आई वांट टू ट्राई ट्रस्ट नो वन, द हंट फॉर क्रिप्टो किंग। ओह, इट्स एन इंटरेस्टिंग नेम। ट्रस्ट नो वन, द हंट फॉर क्रिप्टो। ये डॉक्यूमेंट्री तो नहीं है ना यार, क्योंकि मुझे क्रिप्टो ना आज तक समझ में नहीं आया जिंदगी में। सो आई होप इट्स नॉट अ डॉक्यूमेंट्री। एक तो यार ये चैट जीपीटी ने अपना सर्च फीचर निकाला है ना। व्हाट इज इट? इट्स, आई होप इट्स नॉट अ डॉक्यूमेंट्री। डॉक्यूमेंट्री है, ओके ओके ओके, सॉरी। क्योंकि समझ में नहीं आता है ना क्रिप्टो की चलता क्या, लाइक बेटर कॉल सॉल भी देख लेता हूँ एक बार। अमेरिकन ड्रामा सीरीज, साउंड्स लाइक अ गुड सीरीज। ओ, 9 out of 10 IMDb रेटिंग भाई साहब, रॉटन टोमेटोज इज 99%। Netflix documentaries are cinemas basically. Okay, okay, okay. I can watch. Schindler's List मूवी भी देखना बहुत सही है। लिस्ट मूवी, Schindler's, ठीक है। सो लाइक काफी टाइम से नहीं, कि वो नहीं होता एग्जिस्टेंशियल क्राइसिस आता है, सो आई जस्ट वांट टू वॉच सम कोई मूवी एंड ऑल, तो वो देख सकते हैं। तारक मेहता देख सकता हूँ एक तो। Schindler's List, 9 out of 10 Rotten Tomatoes, 98%, बाप रे, yes, and that is why I like it. Dogs with cinema feels, so, Netflix docs, okay। डॉक्स लिख रहे हो, मैंने कहा नेटफ्लिक्स का डॉक्यूमेंटेशन, लाइक वो नहीं, कोड वाला डॉक्यूमेंटेशन। इट्स वियर्ड। 1993 का आइसलैंडर्स लिस्ट है भाई। सो बेटर कॉल सॉल इज 2015, ट्रस्ट नो वन इज 2022। क्रिप्टो किंग, बाप रे, आई वांट समथिंग। तो सब कुछ देख लूंगा, बहुत टाइम है अब तो, यू नो व्हाट आई मीन। एंजॉय दिस टाइम बड़ी, और ये बोलूंगा मैं। डू नॉट मिस बेटर कॉल सॉल, ओके। हाय कैप्टन। यप। चलो गाइस, इफ देयर इज नथिंग एल्स आई विल, मास्टरपीस, ओके ठीक है। आई विल लॉग ऑफ नाउ, आई विल नॉट वेस्ट अ लॉट ऑफ टाइम ऑफ योर्स एंड माइन। फिर से कोई मिलते हैं डेटा स्ट्रक्चर, वेरी इंटरेस्टिंग डेटा स्ट्रक्चर के साथ। ऑल राइट, आई विल टॉक अगेन समथिंग वेरी इंटरेस्टिंग। सीएस खेल रहे हैं, हाँ खेलते हैं, थोड़ा खाना खा लूँ फिर खेलते हैं आज। मोहित तू भी आ जा यार, एंड वी माइट स्ट्रीम एज वेल, थोड़ा काउंटर स्ट्राइक अगर आज हो सका तो। मिल रहा है, ठीक है। चलो मैसेज कर देंगे, ठीक है डन। थैंक यू सो मच प्रतीक, देव, स्वानंद, कोई और था ही नहीं क्या? सिर्फ मोहित। थैंक यू फॉर बीइंग हियर गाइस। बड़े लोग हैं, मुझे डिस्टर्ब मत कर। चलो बाय बाय, थैंक यू सो मच गाइस, थैंक यू, बाय, टेक केयर, थैंक यू सो मच, बाय, कीप स्माइलिंग, बाय।